Okay, so today we're going to be starting our organic chemistry. So this is topic 8. So what we're going to talk about in this short organic chemistry introduction topic, we're going to firstly talk about our isomers, so the difference between constitutional and stereoisomers, enantiomers and diastereomers. We're going to talk about configurational diastereomers and cis-trans diastereomers. And we're going to get into the E and Z nomenclature. So this might be a little bit different to what you've done in high school if you've previously done organic chemistry. So we're going to go into chirality and talk about what chirality is. And we're going to be assigning R and S conformation on the chiral carbons. We're going to look at simple organic reactions, in particular mechanisms against SN1, SN2, so that's nucleophilic substitution. We're going to look at carbocations and how their reactivity and stability is influenced by the type of carbocation and the substituents coming off the carbocation. And we're going to look at benzene and the aromaticity and the delocalization of those electrons, and then we're going to look at how the nature of benzenes influences the reactivity of these benzenes. So first of all, your isomers. So we have our isomers. There's two main categories. You've got your constitutional isomers or your stereoisomers. So your constitutional isomers are compounds whose atoms are connected differently. Okay, so constitutional or structural isomers is what we're talking about here. So they're compounds with the same empirical or molecular formula, but the different arrangement of atoms. So we'll talk a bit later about an example of this. In your stereoisomers, you can have enantiomers, which are mirror images, and you can have diastereomers, which are non-mirror images. And your diastereomers can be cis-trans or configurational diastereomers. So here are your constitutional isomers. So what I mean here is that you could have the same amount of carbons, so 1, 2, 3, 4 carbons, 3, 6, 9, 10 hydrogens. You can have it as a 2-methyl propane, or you can have it as 1, 2, 3, 4, 3, 6, 7, 8, 9, 10 again, or you can have it as a butane. So you can have those 4 carbons and 10 hydrogens arranged in different ways. And the way that you know that they're constitutional or structural isomers of each other is you try and name them. So if you name this one here, you've got 1, 2, 3 propane as your root name, and you have a 2-methyl. If you name this one, you get butane. Okay, so when you have oxygens in it, you could have an alcohol or an ether, and when you have nitrogens, you can have an amine coming off the central one or the end one. So it's the same number of carbons, nitrogens and hydrogens, but different arrangement of those. Okay, so if we look at stereoisomers, so they're compounds whose atoms are connected in the same way, but they have a different 3D or spatial arrangement. So these include your enantiomers, diastereomers, your cis-trans isomers. And remember, your cis-trans isomers can occur in alkenes or cycloalkanes. It needs to be some kind of locked conformation. Okay, so what are enantiomers and what are diastereomers? So enantiomers are non-superimposable mirror images. So if you put a mirror here, your S-lactic acid is a mirror image of your R-lactic acid. So they're enantiomers. Diastereomers are non-superimposable mirror images. So if you put a mirror here, this is not the mirror image of the left-hand side here. Okay, so you can see that's not a mirror image. Okay, when we have a look at our cis-trans, so trans is when you've got a functional group on opposite sides across a locked double or triple or a cyclic structure. So you've got one up and one down, and cis is when they're on the same side. Okay, so cis is the same side and trans is on opposite sides. So here we have a 1 up, 1 down, and here we have 2 up. So So we've got Cis-Trans. Okay, so naming Cis-Trans diastereomers, the IUPAC naming method is cis is Z and trans is E. So Z-zame-zide is one way of remembering that Z is your cis, so Z-zame-zide. Okay, so cis is Z, so Z-zame-zide, and it's because it comes from the German word together, and trans is E, and that's from the German word opposite. Okay, so the way we work out whether they're on the same side or opposite sides is we look at the priority of the groups. So if we have two groups coming off the carbons, okay, one will have a higher priority and one will have a lower priority. So if the higher priority is coming off one and the other one on opposite sides, then it's a trans, and if it's coming off the same side, then it's a cis. So there are these Cahn-Ingold-Prelog rules for knowing which is the higher and which is the lower priority. So the first thing you do so the first part of the rule is looking at the compound, okay, seeing what's above and what's below, and then you look at the atomic weight, and the higher the atomic weight, the higher the priority. So if we look here, we've got a hydrogen and a carbon. So carbon's 12 and hydrogen's 1, so carbon will have the highest priority. Here we have carbon and chlorine. Chlorine's 35.5 is the weighting there, and carbon again is 12. So you can clearly see that chlorine would have the higher ranking there because it has the higher mass. So we usually go by atomic number, but if you go by mass number, it's the same thing. You'll see the same difference between them. Okay, so here you can see that the carbon and the chlorine will have the two higher rank. So this one here would be your trans, so it would be E, and this one is cis, so it would be Z. So they're on the same side, so it's Z-same side, so it's a Z. Okay, so what happens if, when you're following that rule, you get two carbons, so they have exactly the same weight on them? So if they have the same weight, you go to the next thing that's bonded to it. So if you look here and you go, okay, well, they're both carbons, you go, oh, well, this carbon has 3 hydrogens coming off it, but this carbon has another carbon, and then that carbon has 3 hydrogens coming off it. So if you extend out, this is a CH and this is a CC. So CC has a higher weighting than CH. So this one would be the highest. If you have this example here, we have CC, CC, CH. This one is CC, CH, CH. So this has got 2 carbons and a hydrogen. This has 1 carbon and 2 hydrogens. So the mass of this one is higher, so it will have the higher priority. Okay, and if they're the same, you keep going until there's a difference. So let's look at an oxygen example. So here we've got an oxygen with a hydrogen versus an oxygen with a carbon. So this one would have the higher weight, so the higher priority. And here we have a carbon, 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 hydrogen, carbon, nitrogen. Okay, and here we have a carbon, hydrogen, hydrogen, chlorine. So chlorine's a lot heavier than a nitrogen, so this one would be the higher priority. Okay, so the last rule is if you have double bonds, you count it as 2 single bonds, or triple bonds, you count as 3 single bonds. So this carbon is bonded to a hydrogen and 2 oxygens. Okay, so it's equivalent to drawing out the structure like this. Okay, so that's how we work out the priority, and in the lecture I would have gone through some practice examples with you on those ones. Okay, so let's look at chirality. So a chiral carbon is a carbon that has 4 different groups attached. So if we look at this compound here, we have 1, 2, 3, 4 carbons, and one of those 4 carbons is chiral. So this first one here is a carbon with 3 hydrogens and a carbon attached. So there's not 4 different groups because you have 3 that are the same. This one here has a CH3, it has H2, so it's got 2 hydrogens coming off it, and then it has a carbon. Again, 2 hydrogens that are the same, it doesn't have 4 different groups. So moving on to this asterisked one, we have a carbon, we have a hydrogen, we have a methyl, we have an alcohol, and we have an ethyl group. So there's 4 different groups. So this carbon here is chiral, and this one here has 3 hydrogens, so it's not chiral. Okay, so sometimes when you've got the larger molecules, it's not as simple as this simple example. You need to look at what the rest of the molecule has. So if we look here, we've got carbon 2, we have a CH3, we have a CO, and then we've got that half of the molecule, and here we have a CH2, 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 so it's that half of the molecule there. And we also have the hydrogen that's not drawn in there. So this methyl carbon is actually a chiral carbon. Okay? So chiral carbons can have R or S conformation. So how you work out if it's an R or S carbon is you look at the priorities of the groups attached. You put them in order, so highest, second highest, third highest, and the lowest priority. You rotate the molecule so that the lowest priority is going into the page. Okay, so into the page. So it's away from you. And then you draw an arrow going from 1 to 2 to 3 back to 1. And you don't include 4. And when you've got the 1 to 2 to 3, if it goes clockwise, it's an R conformation. So you're turning your car in a right to the right if you're going in a clockwise steering wheel rotation. And for an S rotation, you've got an anti-clockwise. So you're turning to the left if you were steering a steering wheel. Okay. So let's have a look at these 2 compounds here. So we have an OH, we have a CH3, a hydrogen, a CO2H. Okay, so this carbon here, so first of all you look at the initially bonded atom. So we've got an oxygen, which is 16, we have a carbon, which is 12, hydrogen, which is 1, and a carbon, which is 12. So we've obviously got our highest priority here, which is the OH, because it has the highest molecular weight. We have our lowest, which is the hydrogen, and then we have these 2 that both start with carbon. So what we need to do is then have a look at what's next to it. So we've got 3 hydrogens versus, it's actually 3 oxygens, because a carboxylic acid has a double bond. So it's a carbon double bonded to an oxygen with an OH coming off it. So there's oxygens there. So oxygens are 16 each and hydrogens are 1 each. So this would be the second highest priority and the third highest priority. Now what you need to do is you need to rotate this molecule so that the hydrogen is going into the plane. Okay? And then you go 1, 2, 3, and you have a look at what's happening to it, and then you can work out if it's R or S. So it's 1, 2, 3 again. Okay, so if we rotate it so that hydrogen's going into the plane, so I'll show you with a model in the lecture how you can think about doing this one here. So we've pushed the molecule. If you think you've got this one coming towards you, this one's going into the page, and this one's in the plane, and this one's in the plane. So we're just going to push that hydrogen back in. This OH is going to come up. This CH3 is going to come down a bit out of the plane, and then this one's going to go to the right. Okay, so we've got this one going up, this one going down a bit, and this one going to the right, and then you go 1, 2, 3. Okay, and so that's going clockwise, so it's an R conformation. With this one here, we're going to push the hydrogen back into the plane. This one will come up, this one will come down a little bit, so up, down a little bit, and then we go this way, 1, 2, 3, and we've got an anti-clockwise. Okay, so you can see these are mirror images of each other. So they're enantiomers and they're an RS conformation. So usually when you have enantiomers, one's an R and one's an S. Okay, so let's have a look at how you can rotate these. So what you need to think about is you need to think about the observer and where your eye is. So if your eye is coming in on this angle here, you're going to see this one going into the page. Okay, this one will be up, this one will be to the right, and this one will be to the left. Okay, so this is up, this is to the right, and this is down to the left. Okay, so it's just thinking about the perspective of the observer to try and put that fourth one into the back of the plane. Okay, and again, I will show you with models how to do this. So conformation, so there's different types of conformations that you can have. You can have chair and boat conformations when you get to your carbohydrates, so your sugars, and these are cyclic structures. This one in particular is your sugar one, so it's a 6, 1, 2, 3, 4, 5, 6 carbon structure. And when you have 6 carbon structure, you can have it in a boat conformation, or you can have it in a chair conformation. So this is a chair. Now, each of these carbons have hydrogens or alcohols coming off them, and they can be in axial or equatorial positions. Okay, so with this one here, anything that's going down or up is your axials, and anything that's in the equatorial position is going sidewards. So we've got equatorial, axial, axial, equatorial, axial, equatorial, axial, equatorial, axial, equatorial, axial, equatorial. Okay, and we'll get more into axial and equatorials when we get into our carbohydrates in biological and physical chemistry, and we start linking them together and talking about the nomenclature of those structures. So here I just want you to get familiar with the structures and understand the difference between axial, equatorial, and chair and boat. Okay, so another thing is steric hindrance. So when you have a single bond, when we look at this projection here, this center dot is the first carbon with the 3 groups coming off it, and then this is going to the second carbon with the 3 groups that are coming off it. So you can have a staggered conformation. Okay, so that's where you have the groups away from each other at their maximum distance, or you can have more of an eclipsed conformation where the front or the back carbon moves so that the groups coming off that carbon are more in line with each other. So when we have this eclipsed conformation, we have more steric hindrance. So hindrance from the steric, steric hindrance. So we've got hindrance when those 2 steric bulk or steric groups come into contact, and it requires more energy to keep it in this eclipsed state. So you can see here we've got our energy, we've got our lower energy when we have the nice 60, 180, 300 angles with respect to these 2 hydrogens. And then as they become eclipsed, if they're rotating around, you have a higher energy. So you get like this wave function of it. Okay. So let's talk about our hydrocarbons. So we know what an alkane is. So it's CnH2n plus 2. So an example is your propane. Okay, so you've got CnH2n. So each carbon has a hydrogen coming off it, and then you have the beginning and the end carbon at the 2 ends that have the extra hydrogens, the CH3s. Okay, so your isomers can be structural or constitutional. So it's just rearranging those carbons and hydrogens. So you could have, for example, either butane, or you can have a 2-methyl propane. Okay, so same number of carbons and hydrogens, but slightly different structure on those. So try naming them, and that tells you whether or not they're isomers. So the types of reactions that these hydrocarbons undergo, so they're just hydrogens and carbons. There's no other oxygens or nitrogens or chlorines attached to them. You can firstly have a combustion reaction. So you can have complete or incomplete combustion. So if you have complete combustion under an oxygen atmosphere, you get carbon dioxide and water as your 2 products. If you have incomplete combustion, you can get carbon monoxide or carbon soot and water. Okay, so things that indicate whether or not a combustion reaction has gone to completion is the colour of the smoke. So if you've got white or clear smoke, you know that you've got a complete combustion. So you've got enough oxygen for all the carbons that are there. If you have an incomplete combustion, you will have black smoke or like a sooty kind of look to the smoke that's coming out of it. Okay, so it won't be clear or white, it will be black, indicating that you've got that incomplete combustion. Okay, so another type of reaction that you can have with your hydrocarbons is your substitution reaction. So this is where you substitute a group, so for example a hydrogen with a halogen. So in this example we have CH4 plus Cl2. Okay, so each hydrogen will get substituted with a chlorine. So your first substitution will be CH3Cl, and then your other chlorine will go to that hydrogen that's been removed. So you'd get HCl as a product. So in this we have a nucleophile, which is nucleo is a positive and phile is a lover, so it loves positive things. So it itself must be negative if it's seeking something that's positive. And we also have an electrophile, which is negative lover. Okay, so electrophile, negative lover, and it itself must be positive. Okay, and we'll look at the mechanism shortly about this substitution reaction. So you can have the substitution occurring in one step where you swap over one hydrogen for a chlorine, or if you have excess halogen available, so as much Cl2 as you need, you can have complete substitution down to CCl4. But this would occur in a stepwise manner. So you'd have one group swapping over, then you'd have two hydrogens swapping over, another one would give you three hydrogens swapping over, and then another one would give you that fourth one swapping over. Okay, so the last one that you get with your hydrocarbons are elimination. Okay, and these usually occur with some kind of catalyst involved. So we've got CH3CH3, and we've got a chromate catalyst in there, and we're getting dehydration. So we're taking hydrogens away from that one, and we've got CH2 left over. So we've lost two hydrogens there. So an example of elimination reaction is your fatty acid synthesis. So we have omega-3 and omega-6 that's unable to be produced by enzymes. So you need to eat it in your diet, but a lot of the other fatty acids can be produced from basic starting materials, so it's just putting in the double bonds in there. Okay, but not omega-3s and omega-6. So we've actually got enzymes that can do this. Okay, so let's talk about carbocations, and what is a carbocation? So the name actually pretty much sums what it is. It's a carbocation. So it's a carbon that is positively charged. So we've got a carbocation. Now, we have a primary carbocation, we've got a secondary carbocation, and we've got a tertiary carbocation. So a tertiary carbocation is when you have a carbocation that has 3 carbon groups coming off it. Secondary, we have 2 carbon groups coming off it, and primary, we have 1 carbon group coming off it. Now, the ability for these carbons to stabilize the positive charge is dependent on the groups that are coming off the carbon. So carbons that have carbons coming off them are quite stable because they can hold that positive charge. So if you think of your tertiary carbocation, you've got 3 carbons coming off that central carbon. So you've got 3 carbons around it that have the vacant d orbitals that can hold that extra charge and help stabilize that central carbon. When you get down to secondary, you've only got 2 R groups that are able or two carbon groups that are able to stabilize that positive charge. So it's less stable because there's less key players involved in that stabilization state. When you get down to your primary one, you've only got one carbon helping out that carbon, so it's very stable. And then when you get down to having no R groups, that carbocation is very unstable, and it most likely doesn't exist. If it does exist, it would be very, very quickly. Okay, so basically we have substitution and elimination reactions. So these can both happen under basic conditions, okay, and it depends on the environment of these reactions. And we'll go a lot more into these reactions in biological and physical chemistry, where we have 6 weeks on organic chemistry at the beginning of the semester. So that's in your September semester. Okay, so substitution, we're swapping a group for another group. So it's a we've got a negatively charged species here. Okay, so it's a nucleophile. It's negatively charged. It will be seeking a positive charge. So we have the nucleophilic substitution. Okay, so we're swapping over these groups. And elimination here, again, we've got a nucleophile removing the proton, and that we've got the electrons from this proton moving into the double bond and the bromine coming away. Okay, so nucleophiles are electron-rich compounds, so they have like your delta negative charge on them, and electrophiles are your delta positives. Okay, so some examples of nucleophiles: water can act as a nucleophile, acetate, ammonia, chloride, hydroxide, methoxide, iodine, cyanide, and hydrosulfide. So you can see they're all got negative aspects to the compounds. So they're a nice set of nucleophiles. So with our substitution reactions, like I said, they're nucleophilic substitution reactions, and they can happen via two pathways. So we can have an SN1 or an SN2. And that's just saying what mechanism or what pathway is that substitution occurring. And there are a few key indicators that can help you to predict whether or not it's going to be SN1 or SN2. So here's a summary reaction here. So if you start with a negatively charged nucleophile, you'll get a neutral product. Okay, so it will donate a pair of electrons to this R group, and the X group will come off. And so you'll be one charge less because you've donated a pair. So now you're neutral. And this will get the negative charge on it. So those electrons have gone on to the X, and now we have a negative charge here. So if you look at these mechanisms here, you can see we've got these curved arrows. So the start of the arrow is where the electrons start, and the head of the arrow is where they're going to finish. So this movement here is showing you that these two electrons are going to make a bond to the R group. And this bond here is going to break, and those two electrons are going to go onto the X. So we have a bond here, and then we have two electrons onto the X. If we have a neutral nucleophile, then it will become positive. So we've got these two electrons making a bond to the R again, these two electrons moving on to the X. Okay, so we've got this nucleophile that's got a positive charge now because it's got an extra bond going to it, and we've got this X minus product. So let's have a look at these substitution reactions. So if you've got an alcohol, okay, you can activate this alcohol as a leaving group by protonating it. Okay, so the lone pair of electrons here will make a bond to the hydrogen, and then the electrons in between the hydrogen and the bromine will go onto the bromine to give it this negative charge, and this will then become the nucleophile for the reaction. Okay, so now we've got this positive water on the carbon here, and that's actually wants to break away because it's got a positive charge. It's not very happy, so it will actually come away from the molecule and leave a carbocation. Okay, so you notice this is a tertiary carbocation that's being produced. So one way of working out whether an SN1 reaction will occur is if the carbocation intermediate is stable, SN1 is more likely to occur. Okay, so what we're saying is compounds that are tertiary will more likely undergo SN1 nucleophilic substitution. So you then have your nucleophile come in, and then it directly attaches to that carbocation. So it bonds, so you've had a substitution of that alcohol to the bromine. So when that bromine comes in, it can come in from any angle because that carbocation has left quite a large gap. So it can come from behind the molecule or from the front of the molecule. And what you actually find is you get a mixture of products. You'll get an R and S mixture of that substitution product. Okay, so SN1 substitution gives you a mixture of R and S, and it happens with the tertiary compounds. Okay, so that's because we need to be able to stabilize that carbocation. On the other hand, we have SN2 nucleophilic substitution. So SN2 can happen with primary or secondary carbons. Okay, so there's more room for the nucleophile to come into the carbon, and the key thing about the SN2 is you have the nucleophile come in and you have a nucleophile come out at the same time. So these two electrons are making a bond to a carbon, and these two electrons are going on to the bromine. So we have what we call a transition state. So it's where one group's coming in and one group's leaving. We never have one group that's come in and before the other group has left. They happen at the same time. And this is what we call our transition state. And so you need to have a lot of room around this carbon for the group to come in and the group to leave at the same time. So it does not happen with tertiary carbons. It possibly second, definitely primary, so we need that room for that to come in. So we've got one coming in and one leaving at the same time. So if one's coming in and leaving at the same time, they'll have to come in and leave from opposite sides. So if one's leaving from the front, the other one will come in at the back. If one's leaving from the back, the other one will come in from the front. So what we actually have is an inversion of the stereochemistry. So if we started with an S, because it needs to come in from the other side, we end up with an R. If we started with an R, we would end up with an S. Okay, so we have inversion of stereochemistry, and we have our non-tertiary carbons that undergo these types of substitution reactions. So SN2 is when you have a transition state and you've got two atoms partially bonded at one time. So that's where the 2 comes from. Okay, so here's some diagrams to help you with that one. So you have your electronegative group coming in. You can see that it's arranged so that this one's on one side of the molecule and there's a little bit of space for this guy to come in. When they both come in together, you'll see these go in a planar conformation, and then you go back to your tetrahedral once this side here is left. So we've got an inversion of that stereochemistry. So in terms of the reactivity, you've got your methyl is highly reactive, okay, and then you've got your primary. Your secondary is not so reactive, and your tertiary is pretty much unreactive. Okay, so the bulkier the group is coming off here, the less likely it is to react. So if this is like a ring structure, that might not be too bad because it would be in the planar conformation, but if these were quite like CF3 groups coming off there that were quite large and took up a lot of space, then they'll be less likely to react. So it's about looking at the reaction and thinking about what factors would influence to go in the forward direction and which factors will hinder it from going in the forward direction. And it's a prediction to work out whether or not that reaction will proceed or not. Okay, so the last type of reaction that we'll look at for hydrocarbons are free radical reactions. So this is where you have a hydrocarbon, for example, CH4, and you have an initiation source which produces a free radical, and then that free radical will go around and propagate a few different molecules, and then we'll learn about how free radical mechanisms quench themselves or terminate. So firstly, what are free radicals? So free radicals are compounds that have an odd number of electrons. So when we've done our Lewis diagrams earlier in the semester, we've looked at compounds that always had an even number of electrons. There was always lone pairs or bonding pairs. We never had a loose electron floating around. So this is chemistry now where we're looking at extra electrons. So examples of compounds that have an odd number of electrons are NO2, SO3-, and NO. So if you actually went to start doing the Lewis diagrams of these and you counted up the valence electrons, you would notice that it's an odd number of electrons. So that's how you work out if something's a free radical or not. So generally for your initiation process, you would have some sort of event occurring to give you the breaking of a Cl-Cl bond. So you'll notice that these arrows here are single-headed arrows, whereas before we had double-headed arrows. So the single-headed arrow is telling you that one electron from that bond is going onto this chlorine and one electron from that bond is going onto the other chlorine. So for this to happen, we would need to have an initiation source, which is usually UV light, and hence where all that aging comes from if you sit out in the sun. So you have your initiation step, followed by your propagation, so your propagation step, and then finally your termination step. So your propagation is when your free radical hits another molecule and makes that molecule a free radical, and termination is when you have two free radicals coming together and their two extra electrons go, oh, let's make a pair, and then they stop propagating. So alkenes. So alkenes are where you have at least one double bond. So if you had one double bond, the formula there would be CnH2n. We've got the ene nomenclature at the bottom, and we can classify these as being unsaturated. So a saturated molecule is when it has the highest possible number of hydrogens attached to each carbon. So now we do not have the highest possible number of hydrogens attached to each carbon because we've got a double bond in there. Okay, so it's now an unsaturated molecule. So remember, with the bonding on these ones, we have our sigma bond and we have a pi bond. Okay, so side-on overlap of your p orbitals for your pi bond and front-on overlap of your s orbitals for your sigma bond there. Okay, so they're sp2 hybridized. So the types of double bonds you can have are cumulative, where they're next to each other. We have conjugated, where you have double, single, double, single, double. And you can have non-conjugated when it's just like a random order of double bonds. So you might have two in a row, then a couple of gaps, and then another one. So it pretty much doesn't fall into cumulative or conjugated. So conjugated systems are the most interesting. So you'll find you'll talk a lot about the conjugated systems the most. So conjugated, so conjugated compounds are important to remember what we're talking about. So double, single, double, single, double. Okay, so with your alkanes you have free rotation around each bond, but now that you've got that pi bond that's involved, we've kind of locked the conformation a little bit more, so we don't have that free rotation around the carbon bond, and as such we can now get cis-trans isomers occurring. Okay. You don't get cis-trans isomers in your alkanes because it can just rotate. Okay, so it's not in that locked conformation. So the things that characterize alkenes over alkanes is the addition reaction. Okay, so because you've got a double bond there, you've got two electrons in there that can react quite easily. So they're happy to add a halogen or add water across the double bond to make an alcohol, or just hydrogens across it, and this is where we get into Markovnikov's rule and the rich gets richer, which we'll talk about again in a minute, and they also undergo combustion reactions with oxygen, so the same as the alkanes do. Okay, so addition, we can have halogenation, so we've got a double bond going to a single bond, and we can add a bromine in, so a halogen, so bromine, iodine, fluorine, halogenation. We can have hydrogenation, where we're adding hydrogens across the double bond to go back to your alkane. Or we can have hydrohalides, where we have an acid of some sort. So a hydrohalide, so we've got our halide and we've got our hydro. So pretty much with your halogenations and your hydrogenations, you've got one bromine going to one side, one bromine going to the other. It's a symmetrical molecule to start with, and it will become symmetrical at the end. So same with your hydrogens. The difficulty arises when you have a hydrohalide. So you've got a H and a Cl, and then you're going to think, well, which side's going to get the hydrogen and which side's going to get the chlorine? So this is when we get into a particular mechanism and we talk about Markovnikov's rule. So this is our addition mechanism. So we have our double bond here. So we've got an electron-rich region. Okay, so the electrons move on to your hydrogen, and you'll make a bond to the hydrogen. And then you'll have a carbocation being produced. And your nucleophile will then come in and make a bond to that positive to quench the positive and quench the negative and make a neutral bond. So we've got our nucleophile coming in second after the carbocation has been formed. So remember your carbocation stability, so we've got our tertiary being the most stable, our secondary being the next, and then our primary. So you can see that this mechanism would proceed via the most stable carbocation intermediate. So the side that is the most stable carbocation would be the side with the more carbons or R groups coming off it, and that would be the side that gets the chlorine. So the side with the less R groups, you could say the more hydrogens would get the hydrogen on it. So that's where we get this, the rich gets richer from, because the side with the most hydrogens will get the hydrogens from the addition rather than the other group, and that is because the carbocation would be more stable, and so the nucleophile will attach to the carbocation side. Okay, so the rich gets richer. So we've got this one here, we've got the breaking of the bond, we've got one side with two carbon and one side with two hydrogens. So the carbocation will form on the carbon side. So the hydrogen will attach onto the hydrogen side. And then we've got our carbocation, and then we've got our nucleophile coming in. Okay, and then this one's actually a water, so we've got to deprotonate the water, so it's a little bit more complicated. And then you'll get your molecule with the side with the more hydrogens got the hydrogen, and the side with the less hydrogens got the oxygen. So when I'm talking about the side with the more hydrogens, I'm talking about the hydrogens bonded to the carbon that's across the double bond. So you look at your double bond, you look at the two carbons, and it's the hydrogens directly bonded to that carbon that will get the hydrogen, the side with the more hydrogens. I'm not talking about these carbons that are one bond away, because they're too far away for this carbon to even recognize what's happening out there. So this carbon here, we're looking at what's directly bonded. We've got two carbons. This carbon here, two hydrogens. Hydrogen will go on this side, and then the OH will go on the other side. Okay, so again, we've got our combustion reactions and we've got our polymerization. So we've got our initiator, our initiation reaction, we have our propagation reaction, and we have our termination reaction. Okay, so here are some examples to work through. Okay, so which side will get the hydrogen and which side will get the chlorine. So I'll give you a little bit of time to think about this. Okay, so looking at our first set here, we've got our double bond here. This carbon has a carbon and a carbon coming off it, and this one has a carbon and a hydrogen that's not drawn in. So we'll get the H2 here, and then we'll get the Cl coming off here. looking at this one here, when we have water we get an OH adding to one side and a hydrogen adding to the other. So this side has the more substituted carbon, and this side has the more hydrogen, so we'll get CH3 on this side, and then we'll get CH3OH on this side here. So looking at this example here, we've got our double bond. This one's got 2 carbons coming off it. This one has 2 hydrogens. So this carbon here will get the hydrogen, and this carbon here will get the bromine. So looking here, we've got 1, 2 versus 1. So this side will get the hydrogen, and this side will get the OH. Okay, so this side with the more hydrogens gets the hydrogens. Okay, so let's have a quick talk about our cell membranes. Okay, so remember, we've talked about this before. Our cell membranes are comprised of lipids, and their unsaturated fatty acids in the cis conformation can introduce kinks into the packing arrangement. So if you've got oleic acid in the trans versus oleic acid in the cis, you'll see that the cis one has this kink in it, whereas this one's fairly straight. So what we find is if we need kinks in our membranes, so we need these cis ones, because otherwise our membranes are packed, the lipids are packed too tightly together, and we don't have the fluidity or the movement across the particular membrane because it's too closed in. So we need to have our cis fatty acids over our trans fatty acids. So another thing that increases the fluidity across the membrane is having cholesterol within it. Okay, so if we have cholesterol in there, again, it's providing a bit more of an uneven packing, so we can have more movement across those membranes. Okay, so trans fatty acids are not good because it packs our membranes, our fatty acids in too close together with our membranes. Okay, so alkynes. So alkynes are just like double alkenes in terms of our reactivity. So they undergo addition reactions. So if you've got an alkyne, it's going to go to an alkene through one reaction, and then an alkene to an alkane if it's in excess. Okay, so if there's lots of that reactant available. And again, because it's a hydrocarbon, it can undergo combustion. So complete or partial combustion depending on the environment of the reaction. Okay, so lastly we want to talk about our aromatic hydrocarbons. So benzene is a really unique and exciting structure, and you'll talk a lot about it when you get into biochemistry, because we've got a lot of benzene rings in our amino acids, and those hydrophobic interactions between the two benzene rings overlaying your catalytic domains and stuff of your enzymes is something that's quite interesting and highly relevant in the medicinal chemistry field. So basically, what is a benzene? So a benzene is a C6H6 structure. So it's 6 carbons, and each carbon has 1 hydrogen coming off it. So it's a ring structure. And it took a while for chemists to first work out what was going on. They knew that it was carbons that were 6, hydrogens were 6 of them, but they couldn't quite work out what sort of bonding was going on. So initial experiments showed that they were unsaturated molecules, and they didn't undergo addition reactions. So it was really confusing. So if you think a double bond undergoes addition reactions, whereas a single bond undergoes substitution reactions. So the reason behind them not undergoing addition reactions is got to do with their stability. So this is how we draw a benzene ring. So you draw a double, single, double, single, double, single. So we say there's a double bond, a single bond, double bond, single bond. But in reality, it's not actually like this. This is probably a more correct way of drawing a benzene ring. So you have what we call a delocalization of these electrons above and below the plane in these p orbitals here. So I like to think of it as a donut. Okay, so you've got this donut shape, and you've got the electron density above and below the plane. So these delocalized pi cloud of electrons provide a great stability over single double bonds. Okay, they do not undergo addition reactions. They do not want to break this delocalized cloud of electrons, but they're happy to do substitution reactions. They undergo what we call electrophilic substitution reactions, and the mechanism is here. Okay, so we've got our benzene ring, we've got our electrophile, and the electrophile will swap out a hydrogen. Okay, so this mechanism I'm showing you now is the substitution of a benzene. So there's nothing that's attached to that benzene, it's just by itself. So what we have is we have the delocalized electrons attacking the electrophile and the formation of a negatively charged nucleophile. So we get this structure here that's formed. We have a carbocation intermediate formed. This is a very slow step. Getting benzene to do this is slow. It doesn't want to do this. As soon as this carbocation is produced, it's removed straight away. So a nucleophile removes the proton, and then these electrons go back into the delocalized cloud system, and you get your electrophile being substituted onto the ring. So this is a very fast step, and this one's a very slow step. So restoring the aromaticity and the nature of that benzene ring happens very, very, very quickly. Okay, so that's all for this topic. It's a really kind of short summary into the introduction to organic chemistry. We will be elaborating greatly on this topic when we get into biological and physical chemistry. So we'll firstly be starting off with substitution reactions and elimination reactions, and kind of talking about this sort of stuff again, but to a greater detail. And then we'll go into the different functional groups. So we'll look at alcohols, and then we'll look at carboxylic acids, and we'll look at amines, amides, and esters and ethers, and pretty much most of your functional groups we'll talk about, and the types of reactions they undergo. So yeah, I'm going to put up some more support material for you. Please make sure that you come along to the classes, because a lot of this topic needs to be shown in 3 dimensions with model kits for you to learn at that initial state. Okay, so happy studies, and contact your convener if you have any questions.